this segment we're going to talk about the Brayton power cycle with regeneration. So how can we increase the thermal efficiency of a Brayton cycle? If we look at our equation for thermal efficiency, we can either mess with the work net out or the Q in. And we're going to mess with the Q in here. We're going to try to decrease it with what's called regeneration. And what that's going to translate to is increased fuel, increased cost savings. All right, so let's kind of back up and just look at a simple Brayton cycle. And we're going to follow along on a TS diagram. We are looking, just keep in mind, we're looking at an ideal cycle. So those compressors the compressor and the turbine operate isentropically. So if we follow along on the TS diagram from 1 to 2, our air undergoes an isentropic compression. And we're going to make air standard assumptions, which means that the combustion process is going to be modeled as a simple heat addition process, and that's going to take place at constant pressure. So that's a line of constant pressure on the TS diagram, and it's going to come out at what we're going to call state 4. I know I missed state 3, but just bear with me. We're going to come back to it in just a second. Then we go through an isentropic expansion within a turbine all the way to state 5. And in a gas turbine engine, normally this is where you have your exhaust, but we're making air standard assumptions in our model, and we're going to model that exhaust process as a constant pressure heat rejection process. So there's my line of constant pressure on the TS diagram all the way back to 1 so that I close my loop. All right, so with the setup that I have here, I have to add enough thermal energy to get myself, or to get that air from T2 all the way up to T4. And the idea behind regeneration is to preheat the air so I don't have to go all the way from T2 to T4. Maybe I go from some point in the middle all the way to T4, and that would decrease the amount of heat that I have to add. And the way that I'm going to do that is by adding a regenerator to my cycle. A regenerator is just a glorified heat exchanger. So if you look at the air coming out at state 5, that air still has a lot of thermal energy, and normally that would just be lost, that would be rejected in the exhaust. But what we're going to do is we're going to redirect some of that thermal energy back into the cycle. So we're taking some of that thermal energy from the very top, 5, 6, and putting it back between 2 and 3. So my Q regen is going to heat my air up to T3 so that the amount of heat that I have to add via combustion is only going to have to bring me from T3 to T4. And then I could also put this state 6 over here. You'll see that as my air goes from state 5 to state 6, it cools down, and so no surprise there. My T6 is less than my T5. Okie dokie. So when I calculate my thermal efficiency, that Q regen does not get factored into the equation. The only thing that gets factored into it is the Q in, because that Q regen, it's just heat that's being moved around within the cycle. It's not leaving the cycle or coming into the cycle. It's just moving around within the cycle as a whole. All right. So one last thing, as we move, or as maybe not as we move, but if you look at the pressure at state 1 and state 6 and state 5, they are all exactly the same, because we're just moving, 5, 6, 1, we're moving through two heat exchangers. And one of the assumptions that we're making with air standard assumptions is that everything occurs reversibly. There's no friction, there's no fluid friction to cause any pressure drops where we don't want them to occur. And the same thing from 2 to 3 to 4. No fluid friction, and so you don't have any pressure drops in P2, P3, P4. All are equal to one another. All right, so let's talk about the regenerator effectiveness. We're making the assumption that everything operates reversibly, and that regenerator effectiveness allows us to quantify the deviation from reversible behavior, because in reality there are going to be irreversibilities. There's no such thing as a completely reversible process. It's just some idealized process that we're kind of comparing to. So here's my equation for regenerator effectiveness. It's equal to Q regen, the actual amount of heat transferred by regeneration, over the maximum possible amount of heat that I could transfer by regeneration. And so to kind of quantify what I mean here, I'm going to just look at I'm going to draw my control volume from around the airstream from 2 to 3. So there's my control volume. I've drawn it as a little red red dotted line. And if I applied my first law to calculate what Q regen is, it would be the first law for an open system, because I've got mass flowing in at 2, mass flowing out at 3. And that Q regen would be treated as a Q out in your first law. So this would boil down to H3 minus H2. But how do I handle that Q regen max? Well, as my air flows from 2 to 3, it heats up because I'm transferring energy within the cycle as Q regen. Ideally, if that regenerator operated reversibly, it would have heated all the way up. By the time that air flowed from state 2 to state 3, it would have heated all the way up to the same temperature as state 5, which is the incoming hot stream, if you want to think of it like that. And I'm going to call that 3 prime. So if I wanted to quantify the Q regen max, that would be H3 prime minus H2. And now for an ideal gas, because enthalpy is only a function of temperature, I notice that 3 prime and 5, so state 3 prime and state 5, they're both at the same temperature, so they have to have the same enthalpy as well. So I could rewrite this equation and replace the 3 prime with 5. So H3 prime replaced by H5, and that just makes it a little bit cleaner. All right, so now let's look at it from the other perspective, that top little part, 5 to 6. So if I applied my first law to that control volume as I've drawn it, that would be, when I apply my first law for an open system, that would be treated, the Q regen would be treated as a Q out, and what I'd be left with is H5 minus H6. So let's see how I handle the Q regen max. Well, as my air flows from state 5 to state 6, it of course decreases in temperature, and ideally it would have cooled all the way down to the same temperature as state 2, the same temperature as the incoming cold stream. Now of course it doesn't, but I'm going to call that point state 6 prime. So if I write my Q regen max, this would be H5 minus H6 prime. And because for an ideal gas, H is only a function of temperature, I could replace that H6 prime with H2, since state 2 and 6 prime are at the exact same temperature. All right, well, thank you very much for watching, and we'll work some problems the next time we meet.